Hi, everyone. Welcome to Back to Break Sit Down. In this episode, I want to talk a bit more about logarithms and exponential models. Okay. In the previous episode, we focused on how you can convert from discrete non-continuous exponential functions to base E continuous exponential functions. And we're going to do a little bit more of that here, just with word problems. Okay, so in problem number 2, the population of a bacteria colony starts at 100 and grows by it goes by 30% per hour. Find an exponential function model for the number of bacteria B after T hours. Okay, so I'm going to write a non-continuous function. Okay, they didn't use that word continuous at all. They said it grows by 30% per hour, so that's a base B function. And it's growing, so that means B is equal to 1 plus R. Okay, so my exponential function will look like this. B is equal to the initial value of 100 times 1.30 to the t power. Part B says, what is the continuous growth rate of the colony? All right, so we need to convert, okay? So like, if I use my little table below, they want me to find the continuous growth rate. And according to the table, that means I need to go K times 100%. Okay, but what is K? I need to find that first. So K can be found by calculating the natural log of B. So that's the first thing that I need to do is I need to calculate the natural log of 1.30 because this will tell me what K is equal to. Once I know that, then I can multiply by 100 to get the percentage. Okay, so I'm going to calculate the natural log of 1.30. I'm going to multiply that by 100, and I'm going to get my continuous rate of 26.24%. So it's all about what do I want to know? I want to know the continuous growth rate. I can find continuous rate by K times 100. But I first need to know what is K, so I need to calculate the natural log of B. A population doubles in size, doubles, every 20 years. Assuming the exponential growth, finding the annual growth rate. All right, doubles. That is a key word. That means I'm working with doubling time. Now it says it doubles every 20 years. Okay, didn't use the C word. So I'm going to write a base B exponential function here. So the formula for doubling is 2 equals B to the T power, right? I know T is 20. So I have 2 equals B to the 20th power. Now, I need to undo this, and this is not an exponential function. This is a power function. So to undo raising something to the 20th power, I need to take the 20th root. Okay, and I can do this on my calculator by calculating 2 to the 1/20th power. Okay, so I did that. And I got a B value of 1.0353. Now my annual growth rate is dependent on B, because if you look at the table for the rate rule for a non-continuous function, it's B minus 1 times 100. That's how I find annual growth rate, B minus 1 times 100. I now know what B is. So if I go 1.0353 minus 1 and multiply that by 100, I'm going to get 3.53% for my annual growth rate. Part B is asking about the continuous growth rate, right? So that involves me knowing what K is, because continuous rate is K times 100. So I first need to calculate K. So K is equal to the natural log of b. So I'm going to figure that out first by calculating the natural log of b. And then once I know what k is, I'm going to multiply it by 100. And that's how I'm going to find the continuous growth rate. So I'm calculating the natural log of 1.0353, and I'm multiplying that by 100, doing all of this on my calculator, and I get 3.469%. Slightly different from the annual growth rate, and it should be. Okay. So let's check out one more example. In this problem here, we're told that the population of Spring Grove grew from 11,000 to 13,000 in 3 years. Okay, that means if we assume that the population can be represented by an exponential function, we can calculate the change factor. So change factor formula is over here. We used this formula quite a bit in the previous chapter. It involves using 2 data points, and we know of 2 data points because we know initially Spring Grove had a population of 11,000, and then 3 years later it was 13,000. So we want to plug these values into our change factor formula to calculate the value of our change factor. So I'm going to say that b, my change factor, is equal to y2 is the 13,000 divided by y1, and then I'm going to raise that to the 1/3 power, and I'm going to throw this whole thing into my calculator because I don't know how to do it off the top of my head. And I got that b is approximately 1.057. So given 2 points, it makes perfect sense to use the change factor formula to find b. Part B asks, what is the annual growth rate? Well, according to our table below, for non-continuous functions, we want to go base minus 1 times 100%. So if I do that with my b value of 1.057, I'm going to get 5.7%. Now, the continuous growth rate, according to our table, is k times 100. I need to know what is k, and so I need to calculate the value of k, which is equal to the natural log of b. So I'm going to calculate k first, which is the natural log of b, and then once I know my answer, I'm going to multiply that by 100. So using, and I'm going to write over here on the right-hand side, so I would say k is equal to the natural log of 1.057, calculate that, and then multiply the result by 100. And when we do that, we get 5.543%. And that would be our continuous growth rate. And so that's how we can combine basically everything we've studied in chapters 4 and 5 about continuous and non-continuous exponential functions. This table summarizes it all. We focused on basically taking b and converting it into e to the k. So we've got our conversion factors, we've got our rate rules, and how we find b, well, that varies. Consult this table if you need to. And that's how Becker breaks it down.